Hello and welcome to this Vivado Quick Take video where we'll be discussing the Processing System Configuration Wizard for Xilinx's new Zynq Ultrascale Plus MPSoC. In this Quick Take video, we will become familiar with the basics of the Processor System Configuration Wizard, or PCW for short. We will learn how to configure key features of the new Zynq Ultrascale Plus MPSoC processing system, and how to take advantage of the auto-generated ANSYS source files to kickstart your software projects. This training assumes that you're familiar with the basics of Vivado, such as creation of block design diagrams and a working knowledge of the PS configuration wizard for Zynq 7000 processing system. In this video, we will demonstrate the PS configuration wizard for Xilinx's new Zynq Ultrascale Plus MPSoC processing system. To get the most of this training, we recommend watching the video building a new hardware and software project targeting the Zynq ZC702 evaluation kit, which can be found at www.xilinx.com. For our agenda today, we will start by demonstrating how to access and invoke the PS configuration wizard for Zynq Ultrascale Plus MPSoC. We will then provide a quick overview of the basic configuration parameters before we highlight some of the new features introduced specifically for the Zynq Ultrascale Plus MPSoC family of devices. The two new features we will be focusing on are the system security and DDR configuration. In particular, we will demonstrate how to set security policies leveraging the security configuration page of the PS configuration wizard. We will also demonstrate how to capture a DDR configuration using as an example Micron's DDR3 8GB device. On completing our configuration, we will show you how to locate and review some of the key auto-generated files which are used to kickstart your software development projects. For our demonstration, let us start by creating a simple Zynq Ultrascale Plus design. Click on the Create New Project from Vivado's Quick Start menu. The new project wizard will appear. Click Next. Keep the suggested project name and project location and click Next. Select RTL project and click Next. We do not have any sources we want to add for this example. Go ahead and click Next. We do not have any existing IP we want to add for this example. Go ahead and click Next. We do not have any constraints either. For this example, go ahead and click Next. From the Family drop-down menu list, select Zynq Ultrascale Plus. From the subfamily, select Zynq Ultrascale Plus ES1. From the list of devices supported, click on the XCZU9EG-FFVB1156-3-E-ES1. Go ahead and click Next. The new project summary will appear. Confirm the settings by clicking on the Finish button. This will now create a new project with the settings you just selected. Let us now create a simple Zynq Ultrascale Plus block design. Go ahead and click on Create Block Design located at the Flow Navigator. The Create Block Design dialog will appear. Accept the default design name and click OK. Right-click on the design diagram and select Add IP. From the list of IPs, type Zynq in the search area. Double-click on Zynq Ultrascale MPSoC from the list. The Zynq Ultrascale MPSoC block will be placed in your block diagram. Right-click again and select Add IP and type AXI GPIO in the search. Double-click on AXI GPIO from the list. The AXI GPIO will be placed in your Design 1 block diagram. Click on Run Connection Automation. From the Run Connection Automation dialog, click on AXI_GPIO_0 and then click OK. The necessary connections will be automatically made between the processing system and the AXI GPIO IP. Run the automation connection again. Click on All Automation and then OK. Our simple Zynq Ultrascale Plus MPSoC design is now complete. Let us launch the PS configuration wizard, or PCW for short, in order to familiarize ourselves with it. Go ahead and double-click on Zynq Ultrascale Plus MPSoC component in your block design. This will launch the PCW. For those of you familiar with the Zynq 7000 PS configuration wizard, you will notice many similarities. Let us quickly review the major basic features of the PS configuration wizard. On launching the PS configuration wizard, you will be shown the PS Ultrascale block diagram. This is a high-level block diagram of all the major subcomponents of the Zynq Ultrascale Plus processing system. You will notice how a collection of subcomponents are color-coded differently to denote the device's major power domains. Components with a light green background are powered by the lower power domain, as shown here, while components with a light orange background are powered by the full power domain. Think of this block diagram as a navigational map of all the major subcomponents of the processing system. Subcomponents with either light green or dark red background are configurable. Double-clicking on any of these components will take you to the configuration page of that component. Let us try this with UR0 by double-clicking on it. You will be automatically transferred to the I/O configuration page and right onto UR0. For this example, let us enable UR0 and then let us navigate back to the main block diagram by double-clicking either on the back button or the PS Ultrascale block design in the page navigator. Go ahead and click on the PS Ultrascale block design in the page navigator. You will now notice a tick mark next to UR0. This indicates UR0 is now enabled. As this is an early access version of the PS configuration wizard, some features are not yet enabled. This will be provided in subsequent releases. These components are denoted by their gray background. One of the key features introduced in the PS configuration wizard for Zynq Ultrascale Plus PS was the Advanced mode. Let's go ahead and enable it. You will now notice the security configuration and advanced configuration pages have been added in the page navigator list. You will also notice a number of red blocks have been added to the PS Ultrascale block diagram. This denotes the security components associated with each major functional block. By double-clicking on any of the red components in the block diagram, we will be taken to the security configuration page. The first time you access this page, you will notice that it will not be populated. You will need to add your security policy entries. Not taking into account the CSU and PSU settings, this implies that up to this point, any master can access any slave device if a physical PS connection is made between them. The security configuration page of the PS configuration wizard enables you to capture all system security settings provided by Xilinx's XMPU and XPPU units. XMPU stands for Xilinx Memory Protection Unit and XPPU stands for Xilinx Peripheral Protection Unit. Both units provide additional security for the entire PS system in addition to the trust zone offered by the ARM APU cores. Let us create a simple security configuration for the Zynq Ultrascale Plus. To start adding your security policies, click on the Press the plus button to create subsystems. You will notice three choices from where you can make a selection. To aid in ease of use, the PS configuration wizard provides three distinct areas. The APU subsystem represents the application processing unit of the Zynq Ultrascale Plus MPSoC. The RPU subsystem represents the real-time processing unit of the Zynq Ultrascale Plus MPSoC. The PL subsystem represents the interface to the programmable logic of the Zynq Ultrascale Plus MPSoC. Let us give the APU subsystem the ability to securely access the first 512 MB of the DDR SDRAM memory space. Select the APU subsystem and then select DDR. You will notice that a new security policy entry has been added to the security configuration page. Let us go ahead and change the size to 512, and then let's change the unit to megabytes. You will notice that the N address field has been auto-calculated. Let us quickly review the options we have in the Trust Zone Settings column. We have three options: Secure, Strictly Non-Secure, and Relaxed Non-Secure. If we select the Secure, then the first 512 MB of the DDR can only be accessed by a secure master, in this case the APU subsystem. If we select it Strictly Non-Secure, then only a non-secure master will be able to access the first 512 MB of the DDR. However, a secure master will not be able to access it. If we select it Relaxed Non-Secure, this means that the first 512 MB are non-secure, but in this instance, both secure and non-secure masters can access it. For our example, let us keep this to secure. Let us quickly review the access settings. We have three options: Read-Write, the APU subsystem, is able to perform both read and write operations from and to the memory region. Read-only. The APU subsystem is able to perform read-only operations from the memory region. Write-only. The APU subsystem is able to perform write-only operations to the memory region. For this example, we are giving the master APU subsystem the ability to both read and write from and to the first 512 megabytes of the DDR. Now let us add one more security policy for the RPU subsystem. And let us make sure that the RPU has secure access to the second 512 megabytes of the DDR memory. Go ahead and right-click anywhere in the security configuration area, select RPU, and then DDR. You will notice how a second security policy entry has been added. As with our previous policy for the APU subsystem, go ahead and change the start address to align with the end address of the APU subsystem entry for the DDR. Change the size to 512 megabytes. We can therefore now see that the APU subsystem has access to the first 512 megabytes of the DDR, while the RPU subsystem has access to the second 512 megabytes of the DDR, and neither can access each other's secure areas. As with most systems, perhaps we want to provide the two subsystems with the ability to exchange data using common memory area located in the DDR securely. Let us go ahead and add 64 megabytes that both systems can access. Right-click on the DDR security policy entry for the RPU subsystem and select the plus add option. Go ahead and change the start address to align with the end of the RPU subsystem entry for the DDR and change the size to 64 megabytes. Right-click the DDR security policy entry for the APU subsystem and select the plus add option. Go ahead and change the start address to align with the end address of the RPU subsystem entry for the DDR and change the size to 64 megabytes. So far, we have added security policy entries relating to the DDR memory. However, the security configuration page of the PS configuration wizard provides you with the option of adding security policies for numerous peripherals, or indeed any other memory types such as OCM. For this example, let us add a Gigabit Ethernet Module 0, GEM0, UART0, and USB 3.0 from our low power domain to our APU subsystem. And then add a GPU from the full power domain too. Let us repeat this process for our RPU subsystem by adding security access to I2C0, CAN0 from the low power domain. Please note that for peripherals such as GEM0, UART0, the trust zone options provided two options only. Those are secure and unsecure. Moreover, the access settings also provide two options only. Those are read-write and read-only. This completes our introduction to the security configuration page of the PS configuration wizard. The PS configuration wizard provides you with the means to configure the DDR controller for your specific DDR memory part in an easy and intuitive manner. We will demonstrate how to build a complete DDR configuration using PCW and taking as an example Micron's MT41K1G8SN-125:A. To access the DDR configuration, please select DDR configuration from PCW. Looking at the DDR configuration page, you will notice that it is split into three sections. These are the DDR controller configuration, the DDR device configuration, which is further subdivided to speed bin and operating conditions, and lastly, the training and board details. Let us quickly review these sections. Go ahead and expand the DDR controller configuration. The DDR controller configuration section defines how the actual DDR controller is configured to be able to address and access the data stored in the DDR SDRAM devices. Let us go through some of the options available. Memory type. Memory type allows you to specify which memory type will be accessed. For this early release, only two types are supported. These are DDR3 and low power DDR3. Effective DRAM bus width specifies the data width of the DDR interface, not including the ECC data width. ECC enables the error correction support. Operating frequency in MHz specifies the maximum operating frequency. Internal VREF enables internal voltage reference source. Disable it to use external VRF pins as voltage reference. Operating temperature specifies the intended operating temperature range which controls the DDR reference interval. The DDR device configuration section defines how the actual DDR controller is configured in relation to the specific DDR SRAM device type used in your design. There are several DDR STRAM types supported, as previously mentioned. For this early release, two types are supported, DDR3 and DDR3 low power. Let us briefly run through the available configuration options. DRAM IC bus width. It represents the width of the individual DRAM components. DRAM device capacity specifies the storage capacity of an individual DRAM component. Bank address count, number of bank addressable bits. Row address count, number of row addressable bits. Column address count, number of column addressable bits. The speed bin and operating conditions define the characteristics of a particular DDR STRAM device. The information affects addressing modes and speed of execution. Let us briefly run through the available configuration options. The CAS latency, or CAS stands for column address strobe, and it denotes the latency in memory clock cycles. It refers to the amount of time it takes for data to appear on the pins of the memory module. The CAS write latency in cycles. The CAS write latency specifies the write latency setting in memory clock cycles. The RAS to CAS delay in cycles specifies the TRCD, which denotes the row address to column address delay time. It is the time required between the memory controller asserting the row address strobe, or RAS for short, and then asserting the column address strobe, CAS for short. Presearch time in cycles. This corresponds to the TRP. Presearch time is the number of clock cycles needed to determine access to an open row of memory and open access to the next row. TRC in nanoseconds. It is the row cycle time. TRAS. It is the minimum number of memory clock cycles required between active and presearch command. TFAW in nanoseconds determines the number of activates that can be performed within a certain window of time. FAW stands for 4 active windows. The training and board details section contains 2 entries to allow the DQS to clock delay and board delay information to be specified for each of the 4 byte lanes. These parameters are specific to every PCB design. The DRAM training. If this option is enabled, the DDR controller performs a PHY training after reset. Write leveling enables write leveling calibration, which adjusts the write DQS relative to the DDR clock. Read gate enables read gate calibration, which adjusts the valid RD DQS window. Read data I enables the read data I calibration, which adjusts the read DQS to the center of the read DQ. DQS to clock delay nanoseconds. The DQS path delay subtracted from the clock path delay. Board delay nanoseconds. The midpoint of data, trace delays average with a midpoint of clock, trace delays for byte lanes. Using the PS Configuration Wizard's DDR configuration page, we will capture a DDR configuration using as an example Micron's MT41 K1 G8 SN-125:A, which denote a DDR3 device. For this example, we will focus on the DDR controller configuration and DDR device configuration. The datasheet for the MT41 K1 G8 SN-125:A can be downloaded from www.micron.com/products/DRAM/DDR3-SDRAM. Looking at the first page of the datasheet, and in particular the device name, we can identify a number of information that is required in order to fill in the controller configuration and DDR device configuration sections of the DDR configuration page. The device part name gives us a lot of information. For instance, 1G8. Let us know the capacity of the device. In this case, it is a 1 gigabit device by 8, which makes this an 8 gigabit device, shown as the first red rectangle in our presentation. We will see a more in-depth calculation in the next steps. The device part name also gives us information as to the speed grade of the device. In this case, it is designated as -125, as in 1.25 nanoseconds, which is the maximum clock period in nanoseconds, in this case, and a cache latency of 11 cycles for a DDR3-1600 speed bin, shown as the third red rectangle in our presentation. We will see more in-depth calculation in the next steps. Micron's datasheet shows an example part number and how to identify specific information of interest. It is important to understand the addressing scheme. The device capacity is expressed in bits. In this case, the capacity is based on the addressable range of the row, column, and banks. The device capacity is equal to the row addressable range times the column addressable range times the bank addressable range times the arrangement. For the MT41K1G8SN-125 column A, we will look at the second column of the addressing table designated as 1 gig times 8. This gives us a row addressable range of 2 to the power of 16, a column addressable range of 2 to the power of 11, a bank addressable range of 2 to the power of 3, and an arrangement by 8. This makes the device capacity equals to 2 to the power of 16 times 2 to the power of 11 times 2 to the power of 3 times 8, which gives us 8 gigabits. It is equally important to also understand the speed bin and operating conditions. The information can be derived looking at Micron's datasheet. The device supports 800 MHz, speed grade of -125, which is 1 over 1.25 nanoseconds, operating frequency, and since we are accessing a double data rated device, the maximum transfer is 1600 million transfers per second. The CAS latency in cycles we can actually derive it by looking at the table one above, third row, third column, which is the target TRCD-TRP-CL, which gives us a CL of 11 cycles. The cache write latency, or CWL, we can derive that by using CL equals to 11, and looking at table 41, we can determine that CLW is set at 8 cycles. The RAS to DAS delay in cycles is equal to TRCD divided by the clock cycle, which gives us 13.75 nanoseconds divided by 1.25 nanoseconds, which gives us 11 cycles. TRC is equal to 48.75 nanoseconds, and TRAS min is equal to 35 nanoseconds. With that information, we can now complete the DDR configuration page. Let us expand the DDR controller and DDR device configuration sections. Start by changing the speed bin and operating conditions. As we previously determined, this is a DDR3-1600 device. Click and select the DDR3-1600K from the drop-down list. You will notice that PCW has auto-populated a number of fields such as the operating frequency in the DDR control configuration to keep the settings in sync. The CAS latency has changed to 11 cycles. The CAS write latency has changed to 8 cycles. The RAS to CAS delay has changed to 11 cycles. The pre-charge time has changed to 11 cycles. The TRC has been set to 48.75 nanoseconds. The TRAS min has been set to 35 nanoseconds. The TFAW has been set to 30 nanoseconds. Please note that even though these settings have been auto-calculated, you are still able to further fine-tune them for your own specific part. Looking back at the settings we calculated when we were reviewing the DDR from Micron's spreadsheet, you will notice the values match. Let us continue by reviewing the rest of the settings from the previous calculations. Looking at the DRAM IC bus width, we selected 8 as in 1 G8 memory, which implies a by 8 arrangement as shown here. Next, we will review the DRAM device capacity. Based on our previous calculations, we selected 8,192 megabits, which is equal to 8 gigabits, as shown here. For the bank address count bits, we mentioned previously that the bank addressable range was 2 to the power of 3, Therefore, we will keep 3 as the bits of bank address count. For the raw address count bits, we mentioned previously that the raw addressable range was 2 to the power of 16. Therefore, we will keep 16 as the bits of raw address count. As we can see, this is now set to 16. For the column address count in bits, we previously mentioned that the column addressable range was 2 to the power of 11. Therefore, we will select 11 bits for the column address count. Let's change that to 11. Having concluded our calculations, please click OK and save the project. Let us now explore how the configuration captured by the PS Configuration Wizard is translated to key embedded software auto-generated files. Create an HTML wrapper for your design by navigating on the Source tabs, select Design_1, right-click and select Create HTML Wrapper. Using the default settings from the pop-up dialog, click OK. This will create the HTML wrapper for your project, which is required in order to export your design and auto-generate the embedded software files. From the main Vivado menu, select File, then select Export, and finally Export Hardware. You will be asked to generate output products. Go ahead and click Generate Output Products. Please note this operation may take a few seconds. Click OK when prompted that the generation of the output products has completed successfully. You will be notified to include the bitstream. Keep all the default settings and click OK. We don't want to generate the bitstream at this point. Now, from the File menu, select Launch SDK. A dialog will be presented to notify you of the SDK launch. Keep all the default settings and click OK. This will launch Xilinx's software development kit. Please note that it might take a few seconds to import the hardware specification. With the SDK launched, you will notice the system.htf content showing the address map of the PS system. Let's go ahead and expand the window. In the Project Explorer tab located on the leftmost hand side, you will see the hardware platform associated with the design you created in Vivado. Double-click on the psu_init.h file to open it in the main pane. This file contains all the definitions required for all the registers supported by the Zynq Ultrascale Plus processing system. Go ahead and double-click on the psu_init.c file to open it in the main pane. This file contains all the functions required to initialize the system. Go ahead and scroll at the end of the file. The method psu_init makes calls to all the necessary functions to initialize the MIO, the PLL, clocks, DDR, peripheral, and security data. Please feel free to explore this further. In addition, the psu_init.html provides an HTML view of the entire configuration of the Zynq Ultrascale Plus MPSoC. Please note that since this is an early release of the PS Configuration Wizard, some fields may not be populated. Let us summarize what we have demonstrated today. The PS Configuration Wizard provides you with the ability to create robust and reusable configurations. The PS Configuration Wizard greatly simplifies the task of creating complex, elaborate security and isolation policies in minutes to suit your designs. The PS Configuration Wizard expedites the DDR configuration, enabling you to connect and fine-tune your DDR part of choice in seconds. The PS Configuration Wizard enables you to auto-generate source files that you can readily use in your software projects for complex and diverse system initialization routines. It is minimizing the elaborate and erroneous task of coding thousands of lines of bring-up code from weeks to minutes. This completes this quick take video on demonstrating the PS Configuration Wizard for the Zynq Ultrascale Plus MPSoC. Thank you for your time.